Hi, I'm Shane McGrath. I've over 10 years experience in data analytics. I've got degrees in maths, economics, and statistics. Today, I would like to continue the video series that I've been doing. So yes, I kind of looked at a field programming gateway array and a transformer applied to that. And now I will look at the positional encoding information in LLM. So this paper was released um, yeah, positional information in transformers, an overview. So this paper was released 2 years ago at this stage, but some of the topics are have become relevant, especially recently. So it's definitely an interesting area. So the researchers wanted to compare methods using standard notation, and they also wanted to use this as a way for researchers to kind of like a reference to spurn research in these various areas. Cool. So the transformer model. Um, so the transformer model has an encoder, decoder. Kind of looked at it yesterday. It processes the encoder differently from processes the decoder. The crucial point about a transformer is that it is invariant to the data. Positionally invariant. What that means is that the transformer itself doesn't realize the differences in position that words may have. Um, the research mainly uses for encoding, but it can also, from what I understand, and I'm still kind of getting to grasp with some of this uh, stuff, some of this tech, I suppose. Um, the transformer doesn't intuitively know the positioning within the sentence. Um, so the encoding this gives the transformer better prediction predictive power. So yeah, this is what the transformer looks like, and this is the encoding block. It's a reel-to-reel mapping, apparently, and I have my doubts on that. But it's no, notationally wise, it's a reel-to-reel mapping. The attention block, there's the softmax, layer norms. So yesterday, you kind of looked at these as different ways to be different kind of operations to be calculated. So this is what the encoder block looks like. There's an attention feed forward, and various different matrices or parts of the matrices get calculated at different stages. The reason researchers bring this uh, up is mainly because this is how the positional decodings are brought into the model, or how they uh, encode or how the positional coding is brought into the model. So order invariance. If we take close look at the transformer model, we see that invariant to reordering of input. So, like I made a video about a very kind of similar topic, which was algebraic structures, uh, invariance, and learning. So the researchers in that paper said that learning was a feature of invariance. So here we kind of see invariance again as a feature of kind of predictive power and learning. So you can kind of see that that uh, this kind of property is not an emergent feature of transformers, but it's definitely key to it's a learning dimension that it needs to be kind of fully kind of understood in order, otherwise it could cause interference could be the word, but or it would be underutilized as well. So yeah, you can kind of see here that they use similar kind of mathematical operations. The transformer, the softmax, and the identity matrix are equal, whereas they shouldn't be equal. Is what they're saying. So it's similar to this kind of group algebra stuff of commutative groups and non-commutative groups. Um, Crucially, from what I understand here, is some of the it, some of the information contained in the sentence or the sequence is lost essentially without some sort of positional encoding or information. So the main points are the reference points. So the how the, from the research here look at kind of words and sentences. So that's the easiest way to kind of refer to this stuff. So absolute reference and relative reference. So absolute is like is where it is in the block, and so it could be an adverb. The example I gave is suddenly at the start of a sentence, and then the relative one could be uh, a more frequently used word. So that would be is perhaps, and then it'd be is a or is the. So you kind of the transform we pick up that relative information. However, the relative information takes less data to for the transformer to encode. However, the research makes the point that there's no statistical evidence for which one performs better. So the next one is injection method. So there's either you inject in the input or in the attention matrix here. So two different methods. One called additional position encoding, and the other one is called uh, matrix. The example here is it's matrix uh, manipulation or something like that. Then learnable does the data itself have these kind of positional codings in the data recurring? So that's a combination of the inject methods and unbound. Kind of talked about this before, where the sequence itself depends on how many tokens is in the sequence, if it can, uh, adhere to these so-called function properties that a, um, a transformer is allegedly supposed to have. Cool. Um, so yeah, here's the yeah. So kind of last, and then the positional information models. So you have reference point and the kind of topic subject. Then the absolute relative and relative. So the reference points, the different generic sinusoidal graphs, decoder, and then the comparison of various different methods, what they look like. So the generic is they have no particular mathematical quality. So they bring up Axios positional models, and here they also talk about flow-based transformer, which I saw a paper on yesterday in which these roboticists use a flow-based transformer method, which is a continuous sequence of type steps using a differential modeling equation here. Crucially, this is the sinusoidal positional embeddings are a special case of this dynamic model. So this is a more kind of adaptable, I suppose, form of that. It's encoded into each of the layers, is what they said, layer wise, additional positional coding. Um, so this seems to be a kind of very dynamic positional encoding. as you see, the paper was physical intelligence, and it seemed to be able to do all sorts of clothes 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 folding and things like that. Uh, yeah. Okay. Cool. So this is yeah. So this is the unitary positional coding. So this is just more of a picture. You can see how positional coding kind of looks like, depending on the biases. Suicidal. So this is kind of something that I've been kind of interested in, which was the kind of costs and signs. So this is, as opposed to encoding the layers, it's more encoding the data. I said it's famously in the transformer paper itself. There's many different methods to 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 look to to kind of there's rotary positioning encoding. The main feature about this is that it can arbitrarily handle lengths of any sequence length. So crucially, I think that, like this is me guessing that something like this sinusoidal, the actual like advantages of it don't become apparent until you get more and more data, and then the other methods such as absolute or methods or even axial or things like that, they start to the transformer itself there's more interference or the properties don't hold up. However, these ones are quite mathematical and they presumably would take a lot of uh, planning or testing. So the other ones are easier to implement, but as the transformers get more and more complicated, you have to use some of these more not mathematical but uh, technical methods in order to maintain stability, especially over longer sequences. And that is the intuition that I'm understanding from this. So there's another one is graphs. There's trees and arbitrary. So trees kind of look like the sequence is mapped onto like a tree-like structure. And then there's arbitrary, which is it looks more like some set of groups. So I didn't look too much through this, but it's in the paper if anybody wants to look at this. And then yeah, so this is the comparison of different methods. So the researchers just look at BERT, Roberta, GPT-2, and sinusoidal. So you can kind of see how positional coding, sinusoidal, there doesn't seem to be that much or interference. GPT-2, there's less. BERT and Roberta, it's a bit more kind of cloudy, as you might say. But you imagine that the Burn and Roberta might be easier to train models, and then GPT-2 and Sinusoidal might it might be a lot more kind of pre-data preparation and that sort of thing. So yeah, as I said, it's an interesting paper from a few years ago. So some of the stuff may not be as relevant, and some of the stuff is definitely quite relevant, especially the flow-based transformers, which seem to, as I said, I think they were mentioned along with diffusion transformers. The diffusion, I'd actually see it at all mentioned here as a positional. Encoding or persistent information technique. It seems to be more the sinusoidal. It seems to be the kind of not the kind of basis for some of the more not advanced techniques, but as I said, the arbitrary sequence length is definitely a key feature. Cool. That's me for today. Thanks for watching.